For so long, a major spinal cord injury has felt like, well, a life sentence, a problem with no solution. But what if the secret to healing it wasn't in a lab, but inside a computer? Today, we're going to dive into a really cool, groundbreaking approach that uses a virtual battlefield to figure out the absolute best way to fight back.
Okay, so before we get to the solution, we really need to understand the problem. Why is the spinal cord so incredibly hard to heal? It's a question scientists have been banging their heads against for decades. And the answer is kind of shocking. After an injury, the area doesn't just sit there broken. It actually becomes, well, hostile to any kind of repair.
All right, let's zoom in on what happens right after an injury. It's not a quiet scene. It's chaos, a full-on biological battleground. And here's the crazy part. The body, trying to protect itself, ends up building this massive wall that actually stops any chance of recovery.
Yeah, scientists have a fancy name for this wall, the inhibitory milieu. But you can just think of it as a toxic mess. It's a mix of cellular junk and scar tissue molecules, things like CSPGs, that create this barrier. And they don't just block the path. They're like screaming stop signs that actively prevent nerve cells from even trying to regrow. But every good story needs heroes, right? And in this battle for the spinal cord, scientists have two major players they can send into the fight. Two forces that can potentially tear down that wall and start rebuilding.
First up, we have growth factors. The easiest way to think of these is as the fuel. They're proteins, like NGF, that basically act like a turbo boost, screaming, grow, at the damaged nerves. But, fuel's no good without an engine and a driver. That's our second hero, the grafted cells. This is our construction crew. These are special cells that are put into the injury site to literally rebuild the bridge and make sure any new connections can actually work.
So we've got our good guys, the fuel and the crew, and our bad guy, the wall. But here's the million-dollar question. How do you use them? Just throwing everything in at once? Well, it just doesn't work. This is where things get really cool. We're moving from the lab into the computer to a virtual battlefield where we can test every single strategy imaginable.
And that virtual battlefield is what's called a computational model. Now that sounds complex, but at its core, it's just a bunch of math that perfectly simulates what's happening in the body. The real power here is that you can run thousands of what-if scenarios. What if we use this dose? What if we wait 3 days? It lets you find the absolute best plan of attack super fast and with zero risk.
You can actually think of this whole model as a game with 4 basic rules. Rule number 1, axon growth. The crew can't build their bridge without enough fuel, and only if that big wall is broken down. Rule number 2, wall decay. The wall does crumble a bit on its own, but hitting it with fuel, those growth factors, makes it break down way, way faster. Rule 3 is easy. Fuel supply. More infusion, more fuel. But rule 4, this one's critical. Crew survival. The crew loves the fuel. It helps them thrive, but they're hurt by that toxic wall. So you see, it's this incredibly delicate dance.
Okay, so with the rules of the game set, the researchers could finally get to the main event, running simulation after simulation to find the one single winning strategy. And by doing this over and over, they finally cracked the code.
And the results? Wow. They were absolutely night and day. A standard strategy, just giving a steady dose, it might get you, 25% of the way there. But the strategy the model figured out, it had a 92% success rate in the simulation. That is just a staggering difference. And it all boils down to 2 things, timing and dosage. So what does this winning strategy actually look like? Well, it's a 3-step plan. First, you start aggressive. You hit the site with a high dose of growth factor, around 50 nanograms a day. But here's the twist. The goal here isn't to grow nerves, it's to smash down that wall. Then, once the wall is down, you move to step 2, taper to maintenance. You back off the dose to a lower, steady level. This is when you're actually fueling the nerve growth. And finally, step 3 is all about sustaining that support, keeping that construction crew healthy so they can finish the job.
And this is the key takeaway, the big aha moment. It's all about synergy. It's not just about adding the good stuff, it's about the order you do things in. You have to demolish the old broken building before you can start construction on the new one. The fuel works best only after the wall is being torn down. They have to work in perfect harmony.
So what does this all mean? Well, this is way more than just a cool computer game. This win in the virtual world gives real-world scientists a clear, tested roadmap. It could literally save years, maybe even decades of trial and error research. Let's just stop and think about that number again. 92%. You have to understand, in this field, progress is usually measured in tiny, tiny steps. So seeing a number like this, even in a simulation, is a massive deal. It's a game changer. It tells us that a real working strategy might not be a pipe dream. It's a solvable puzzle, and now we have the blueprint.
So, what can a researcher and a lab do with this information, like tomorrow? Well, the model provides a super clear to-do list. Number 1, try the high dose then taper strategy. Number 2, make it even stronger by adding in enzymes like chondroitinase that are specifically designed to eat away at that scar tissue. 3, make sure you're doing everything you can to keep that crew of grafted cells alive. And 4, use advanced imaging like DTI trachography to actually watch the repair happen in real time.
Okay, and this is a really important point we need to make. This model is not a cure that's ready for patients, not yet. Think of it as an incredibly detailed map. Its job is to show scientists the fastest, most promising route to take, helping them design smarter experiments that get us to a real treatment much, much faster. And that kind of leaves us with a huge, fascinating question, doesn't it? For all of history, medical breakthroughs happened in a wet lab, with test tubes and microscopes. But what if this is a sign of what's to come? A future where our biggest medical victories are won inside a computer first. Could it be that the cure for some of our most impossible injuries starts not with biology, but with a single line of code?